Hello, and welcome to another IB Math Speedrun with me, Vince. So, we're going to be continuing our exploration of implicit differentiation, so let's jump right in. So, the second way we can apply implicit differentiation is, excuse me, to solve equations, to solve something called a parametric equation. And a parametric equation is when we have two variables, yeah, we have x and y, but they're both expressed in terms of a third variable. For example, y is equal to 2t and x is equal to t squared. And sometimes it's hard to express y in terms of x, or it's just harder than what we can do instead if we want to get the derivative dy over dx. So we need to know that dy over dx, of course, is equal to dy over dt times dt over dx. And so if we wanted to differentiate this example parametric equation, well, what's dy over dt? dy over dt is equal to 2, and dt over dx is equal to the inverse of dx over dt. So we can get dx over dt and then divide it. So that would be 2t, so this would be 1 over 2t. So if we wanted to get dy over dx, this would be 2 times 1 over 2t. So this would be equal to 1 over t. So dy over dx is 1 over t, expressed not in terms of x, but in terms of t. So if we wanted to, then we could therefore substitute x into there and get it in terms of x. So as you can see, it makes it easier to solve some equations. So let's jump into some problems. I believe this is the final exercise for this chapter, and then afterwards we're going to move on to the harder exam style problems. I will be doing the uh let's just say the even ones. These are long word problems. Why not do some evens? Okay. So first, if L, W, and H represent the length, width, and height of a rectangular box, express the rate of change of the diagonal length of the box in terms of the rates of change of L, W, and H. Okay, so we need to first construct an equation for the diagonal length of the box, and that would be the diagonal length, let's call it D, is equal to the square root of the 3. So L squared plus W squared plus H squared. So if we want to differentiate this with respect to time, say D, this is probably not a good variable name. And writing this as 1/2. Well, what would we get? We would get 1/2 times, if we differentiate this inside, this is 2L times dl over dt plus 2W times dw over t plus 2h times dh over dt. So we can simply say this is going to equal L times dl over dt plus W times dw over dt plus H times dh over dt times, or actually I guess it's more divided by L squared plus W squared plus H squared to the power of 1/2. Yeah. So that should be it for this one. Yeah, that's correct. Okay, so on to the next problem. And so the next problem is 10-meter long industrial ladder is leaning against a wall on a building site. The top of the ladder starts to slip down the wall at a rate of 0.5 meters per second. Determine how fast the foot of the ladder is moving along the ground when it is 6 meters from the wall. Okay. So we need to construct two equations. First of all, one relating the top of the ladder starts to slip at a rate. So if we say that this is x and this is y, then we have dy over dt is equal to negative 0.5, right? Because it's falling down, and so the y value is decreasing at a rate of 0.5 meters per second. We also have another equation, and that's the square root of x squared plus y squared is equal to 10, since the ladder is 10 meters long. So if we were to, sorry, this is not dy over dx, this is dy over dt. And so we need to find dy over dx from this equation, actually. So we get that x squared plus y squared equals 100. And so, actually, what would this be? Let's just implicitly derive it. 2x plus 2y times dy over dx is equal to 0. So dy over dx is equal to negative x over y. So we need to get the rate, how fast the foot of the ladder is moving along the ground when it is 6 meters from the wall. Okay, so, well, we need to get the rate dx over dt, and we know this is equal to dx over dy times dy over dt. So this is equal to negative y over x times 0.5, sorry, negative 0.5, since that's, yep. And so we should get y over 2x as the rate. So the foot of the ladder is, I believe we have to get how fast it's moving when the foot of the ladder is 6 meters, is 6 meters from the wall. And using this equation, we can also get the y value at that point, and that's when the y would be 8, since 6 squared plus 8 squared equals 10 squared. So the rate would be, y value is 8 over 2 times 6 is 12, so this would be 1/3 meters per second. So the foot of the ladder is moving at 1/3 meters per second outwards at this certain point. Is that correct? Yeah, that's correct. Okay, on to the next one. And so the next question is, a closed right circular cylinder's radius is decreasing at a rate of 3 centimeters per second. And its height is increasing at twice the rate of the radius. Determine how fast the cylinder's surface area is changing when its height is 10 centimeters and its radius is 12 centimeters. So we need to link the surface area to, I guess, the height and the radius. Is that correct? Closed right circular cylinder's radius, decreasing height, increasing cylinder surface area. Yeah, so no, we need to just get, the radius is decreasing at a rate of 3 centimeters per second. So we can say dr over dt is equal to negative 3. And its height is increasing at a rate, at twice the rate of the radius. So dh over dt is equal to 6. And a cylinder's surface area is 2 pi, what is this, 2 pi rh plus 2 pi r squared? Is that the surface area? I think so, yeah. And so this is the surface area, so we need to determine how fast the cylinder's surface area is changing. So we have ds over dt is equal to, this would be 2 pi r times dh over dt plus 2 pi r times 2 pi h times dr over dt plus 4 pi r times dr over dt. So we know that the radius is decreasing at -3 and the height is increasing at 6. So we have 2 pi r, dh over dt is 6, so this would be 12 pi r. 12 pi r. Dr over dt is -3, so this would be -6 pi h plus 4 pi r dr times dr over dt. So this would be -12 pi r. No, that doesn't seem right. Hello, I'm back, and I thought I made a mistake, but apparently I did not. Apparently, the answer is just to completely disregard the radius and get that the rate of change in the surface area is simply equal to -6 times pi times the current height. So since we need to get how fast the area is changing when the height is 10 centimeters, it's simply -6 times pi times 10, or -60 pi, which is equal to -188.5. But technically, since we're expressing it as a rate of change, this would be absolute valued, so this would just be changing at a rate of 188.5 centimeters per second. So yeah, okay, on to the next question. And the next question is, air is being pumped into a spherical balloon at the rate of 7 centimeters cubed per second. Determine, not determine. Find the rate of change of the balloon's radius in terms of pi when the volume of air in the balloon is 36 pi centimeters cubed. I don't know why it keeps changing. Like, oh my gosh. I cannot. Let's type it out again. Sphere, balloon, at the rate of 7 centimeters cubed per second. Find the rate of change of the balloon's radius in terms of pi when the volume of air in the balloon is 36 pi cm cubed. Okay, so we clearly have two equations here. First of all, the volume is increasing at a rate of 7 centimeters cubed per second, so just 7. And we need to find the rate of change in the balloon's radius. We know that the volume of a balloon, if it's perfectly spherical, is equal to 4/3 pi r squared cubed. Sorry, 4/3 pi r cubed. So we can simply relate this directly. So if we get the dv over dr is equal to 4 pi r squared. And so we need to get the rate of change of the balloon's radius. So dr over dt is equal to dr over dv times dv over dt. So this will be equal to 7 over 4 pi r squared we need to get it when the volume of air in the balloon is 36 pi centimeters cubed. Okay, so the volume will be 36 pi centimeters cubed when the radius is divide that. This is 36, 9 times 3 is 27. Wait, that's too big. Oh, 27 cubed, so this would be 3. So it's when the radius is 3. So this would be 7 over 4 pi times 3 squared, which is 9. So this would be 7 over 36 pi, I believe would be the rate of change. Yeah, that's correct. Okay, so on to the last question. And so the last question is a spark from a fireplace burns a hole in a newspaper. The initial radius of the hole is 1 centimeter and its area is increasing at a rate of 2 centimeters squared per second. Find the rate of change of the radius when the radius is 5 centimeters. Okay, so area is increasing at a rate of 2 centimeters squared per second. So dA over dt is equal to 2. And we also, when the radius is 5 centimeters, so dr, so we know also that a is equal to pi r squared. So d dA over dr is equal to 2 pi r. And we need to find the rate of change of the radius when the radius is 5 centimeters. So the rate of change in the radius, dr over dt, is equal to dr over dA times dA over dt. In other words, it's equal to 1 over pi r. Yeah. So when the radius is 5 centimeters, this should be equal to 1 over 5 pi. Yeah, that's pretty simple. So that was all for these speed runs. And I hope you enjoyed them, and I hope you stick around to look at the chapter review where we'll go through a lot of questions. See you then.